Hello and welcome. I'm not sure if it got any of that yet. As you know, I'm terrible with tech, and I thought I was live streaming for a little bit already because I had it live streaming through one of the apps, but I hadn't clicked go live yet, I guess. Here we are, though, in the combo classroom. Unfortunately, we missed a squirrel in the intro. A squirrel came and I did feed it a nut, but I've been saving up my squirrel clips that I film, like a squirrel saves their nuts, for an episode that will occur at some point in grade -2 of combo class about all the rare animals that visit our classroom. Like, hey, look, there's Dandelion. Dandelion! There's Dandelion. But we are about 3/4 of the way through grade -2 right now, and yes, the background does look more destroyed than ever. This planter bin that was filled with dirt and had an actual bottom got most of its demise. I guess part of it's still there, but mostly shattered in the last combo class episode, which I put out last night. Many of you have probably not seen that yet because it just came out like half a day or so ago. So that is linked in the description. Make sure to catch that if you have to leave the stream or if you watch the whole stream and it ends. Because eventually it will end, and that combo class episode is even better because that's one of my favorite ones I've made yet. Has a lot of clock-like math. And also, you will see why that thing breaks, or how. It was already on its way to its demise, and for those who wonder, does it cost me a lot that a lot of stuff breaks around here? No, I get my classroom supplies, some of which are more of props, for very cheap or free. So don't worry there. Now, in today's stream, I wanted to look at sort of a follow-up to some of what we've talked about in previous streams, but don't run away if you weren't here for those. Even if you're starting from scratch, this will make sense. And it is sort of the last for people who do follow all my stuff, but are bored of the numberation card game ideas I've been discussing recently. This is the last stream we'll do about those for a minute. And I was already going to pause on those and move on to other topics of streams, but, well, I did continue to work on the game on my own. But I have a few important updates or innovations about this game. You see, for one, people asked about physical cards. I mentioned that I'd made physical cards so that I could test out the game with friends and family and such, or even on my own. Or with the ghosts and demons. But testing out the game, I couldn't find my test cards during the last stream. Here they are. I did bring the test cards that I have designed for the game. They do not include all of the numerations that will be included in the game because there's other innovations and updates I've had. One of these updates that is a variety of other numerations that we can add without shattering the fact that the game will, basically things that add without subtracting, which is difficult to do when you're putting together a game. If I add a new card, I need to make sure it fits in with the whole web of previous cards, and each new one I add has a bigger web to fit into. But essentially, in this game, well, and finally, the last update, apart from having physical cards I'd like to show a demo version of the game with, and having a few more numerations that I've come up with that fit in very well, including ones that do things like a digital complement. We'll see what that means in a bit. But also, we are going to look at how it just struck me about a day ago. There's a cool graphic representation for most of the numerations in my game, and there's a way we can look at a graph, and it will actually describe possible strategies in the card game. And the card game doesn't seem graph-like right away, but you can make the connection if you think about it for a moment. A lot of the numerations as cards are here. Well, first of all, what's a numberation? It's my nickname for I came up with the nickname to mean an operation followed by a number like times 2, doubling, to the power of 2, squaring, minus 2, subtracting 2, things like that. But a numberation could theoretically be a function that takes one number and spits out another number. And in our game, we need to make sure that the function for 1 can cover all of the whole numbers from 1 to 99, are numbers that we might be dealing with in this game. And second of all, we need to make sure at least for the starter version I'm designing for this game, I want each card to have an inverse. Something that if you played one card, then there's another card that played on top of it would have the opposite effect of it and would cancel it out. There are a few that are their own inverse, but most of them need an inverse. Like +1's inverse would be -1. Squaring's inverse would be taking the primary or principal square root. And then other things would be like, you can imagine doubling something. The inverse of that is halving it. We want each thing to have an inverse here, and that means we want our function to be what's called bijective in this range of numbers, where each input lines up with just one output, and that output only lined up with that one input. Like if you had a bunch of chords and you had a bunch of places to plug the chord into, and you need to make sure that every spot that could have a chord got plugged into, and every chord obviously can only go to one. But some functions are not chords. One thing could go to multiple things possibly, or multiple things could go to one thing, like how if we included negative numbers, which would be in a future version of this game, as well as things like complex numbers. If we included those, then, like squaring -4 and 4 would both lead me to 16. And so then it's kind of like, well, inverses get trickier there. That's part of why I didn't include negatives in the starter version, was wanting to have an inverse to everything. And because of these inverses, we're going to be able to make half as many lines on our graph and get as much data. So what do I mean by graph? Well, let's see if this is working. Sometimes I boot up the background and then it doesn't actually show it on stream, so I have to wait a second because the stream takes a second to send from my computer over there. So now I gotta wait 1 second to see if it actually changed the page when I changed it. Yes, it did. We are actually working. So here's an example of how, I think actually, I'm sorry to leave the graphs as like a cliffhanger for a moment, but we're going to do those a little bit later in the stream, because I do want to first just show an example game and explain the principal rules of this game. So essentially what we've been trying to do is each player may have some of these numerations in their hand. The rules, to be specific, are that at the end of your turn, you draw 2 cards, and that during your turn, if you have a valid numberation to play on something, which we'll see what that means, that you must play at least one numberation, and you could play multiple one at a time if you wanted. Now, players have these in their hand, things like ×2, square, and some of the stranger ones that I'll explain in a moment, like the digit reversal or digit complements. And there are 2 starting out as essentially invisible, but then having cards put on them, piles. One of them starts out representing the number 1, and one of them starts out representing the number 31. That's a fun coincidence because this is a pre-Pi Day stream. Pi Day is one of the few mathematical holidays that ever gets talked about. And as a channel that talks about a lot of math and likes holidays, that's pretty cool. Now, I have some mild beef with how they've decided to put Pi Day because I have beef with the calendar system. But that's not beef with Pi. We may discuss that tomorrow. I'll put out some sort of Pi-related content tomorrow, probably. But today, we are doing a pre-Pi Day stream, and in some time zones, it may already be Pi Day for you. They call it Pi Day because it's March 14th, which on some calendar systems looks like 3/14, the beginning of Pi. Speaking of which, maybe if we're bored, someone remind me if you want later. I saw that when you try and Google something, they have this Pi memorization-based game. And if we run out of like more important things to do in the stream later and still want to do more stream, we could do the Pi memorization-based game because I'll slay at that. I already have the first 100 digits or so of Pi like half memorized from when I memorized them as a challenge with my friends back in middle school. And now I could probably recite 3.14159265358, and then I would be a little less sure of myself after that. That's more than enough accuracy to calculate the radius of anything, don't worry. And so the coincidences are not just that 31 starts with 3-1, but also that the cube root of 31 is remarkably close to Pi. It is one of my favorite it might be my favorite approximation of Pi. You may have heard of 22/7 as an approximation. Well, let's go to an online calculator and see how 22/7 fares. That's a fraction you could memorize, 22/7. And that's 3.14, about 3 there. That would round 2/8, about 3, so about 3.143. It says 2, but you know what I mean if we rounded the 8, it has an 8 after it. However, if we look at cube root of 31, 3.141, and then about 4. Pi is 3.1415. That's accurate to almost 4 decimal digits and fully to 3 after the decimal point. So cube root of Pi, that's your way to go. And for those who saw my episode about continued fractions, this is part of why I love Wolfram Alpha as a graphing Desmos is our graphing calculator we're using. Wolfram Alpha just as a general calculator because they will tell me things like this. This is what I didn't know. Where Pi lands on the number line. No, I'm kidding. They'll tell me things like this. The continued fraction of Pi. They'll also tell us some rare things like the cube roots in different strange forms. The third roots that aren't principal. Because for this one, I would recommend... the closest thing I've done to this is my episode about the clock hidden in the number 1, about the roots of unity. So these are the other, on the complex plane, Pi's approximation is not the only cube root of 31. It has friends. So these are some things that make 31 connect to Pi. Somebody said, isn't it 3:13 today, not 3:14? And yes, we're here where I am. It will be 7 more hours until it is technically Pi Day. So very unlikely the stream will last till Pi Day on my end. But I bet that other people will probably have Pi hit their time zone. Some viewers or another will be in a Pi zone where the Pi hits the Pi. Now, the reason I mentioned 31 is not that its cube root happens to be near Pi Day. That's just a fun coincidence. The reason I mention it is because with the numberations I had calculated for my starter deck, I found that 31 was the smallest number that would take any player at least 4 cards to achieve any points in the way I'm about to describe. And I didn't want a player to be able to, in their opening hand, be able to automatically win if they drew the right cards. And I wanted to not get as far from that as possible, almost, where I wanted it to be like whatever cards you draw at the beginning, you're not necessarily screwed. You could play your way into the right spot by the time you have to wait to draw the right cards you want. And I don't want the cards to be better or worse than each other necessarily either. The cards that make something change in size a lot may have less numbers they can affect because, like I said, the only numbers we are going to be using in this starter version are the whole numbers from 1 to 99. We can think of 0 through 9 as being 0, 1, 0, 2, and etc. If we want to think about why that's our clump, sort of. It's all the 2-digit clusters if we count a 0 at the beginning as allowed. So in base 10, we're stuck in base 10. I wish I could make this game in base 6, but so many fewer people would learn the rules and have any attempt of playing it. So maybe someday we'll make variations that are fully in base 6, and then the things like digit reversal will be reverse the digits of this in its base 6 representation and go to that number, as opposed to base 10, but I think the game will be a lot catchier if I have things like swapping the digits just look like swapping the digits in the system that we are stuck in. So it is, a few of them are base 10 centric. The ones we're graphing aren't, and it would actually be hard to make an equation on a graph care about a base. You'd have to, in particular, come up with a really specific equation for a graph to be base dependent. Almost any graph that you would encounter in the wild of mathematics, would be base independent. It wouldn't care whether we're counting in base 6 or base 10. If I graph y equals 2x, it's going to look the same. Now, they're writing it in base 10, but we could think of this as the quantity 2. All of our inputs have to be written in base 10, but any base could, hopefully be able to express the number 2, and then whatever that base wrote it as, x here, will make this line. So most graph shapes would be base independent. Now, let's first start by setting the zone we're going to be looking at. It is only whole numbers, so it's grid points on a certain scale. Like, this would be if I'm at 2, this would be if I'm at 3, and we'll explain what the x and y axes mean. And the way it's going to work is if I want to see how 2x affects a number, this is a numberation I could play theoretically, is doubling something. Well, I could go to the x coordinate of 2, and I can see what y says. Oh, no, wait. This is the wrong scale. This is the scale where ones are doing that. I could go to the x coordinate of 2, and the y coordinate tells me what doubling does. And the reason why I said we need half as many equations is because I don't need to write y equals x over 2, even though that's a numberation. Because since that's the inverse of this, what I also will let myself do as a move when we're calculating it on the graph is go to a y value as an input and see what x says. And this one would be representative of the inverse of that numberation, which in this case is the other numberation, y equals x over 2. Now, back to how the game's rules work. We're going a little back and forth, but that works. Now, there are 2 invisible piles that then will have cards stacked on them and become visible, and there will be a stack of numerations on that pile, and depending what number the pile starts on and what the stack of numerations are, each applied one at a time in ascending order to see what number you're currently at. Even if you forget the number in the pile, you should be able to look at it, look through it without changing the order, and see based on the stack what number you're currently at. And it's not applied in any PEMDAS, BEDMAS order. They go one at a time in ascending height. So one pile starts at the number 1 and one starts on the number 31. And your goal is during your turn, at which you must play one or more numerations. And if you can't play any valid ones, then you skip. There could be a chance that the cards in your hand don't validly apply to a number on either pile to turn it into a whole number in the range 1 through 99. For example, you can't times 2 a 60. You can't divide by 2 a 3, stuff like that. Now, our goal is to make the piles represent the same number during your turn. And then you get as many points as are in the piles. They're swept clean. If you're playing physically, each card basically is a point. So you have the cards each to be 1 point. If you're playing digitally, it might like auto reshuffle the deck to make memorization less important and tally how many points you got based on how many cards were in the piles when they get equal. Basically, when they're equal, whoever's turn it is gets them. So, an example game, if we already had a bunch of stuff in our hand and a bunch of stuff had gone on and we're not necessarily playing smart, could be like, and some of these changed. A few of these got kicked out. And N plus 10 and N minus 10 you might see in the mix. Those are not quite how we're doing it anymore. Those did not maximize how many numerations I could have in while having an ideal number for one of the hills to represent. And a lot of players will want other target numbers. I will provide a list of other target numbers as I study them, of other ones that work well. But 31 already works so exceptionally well. And then I kept adding numerations, and it still kept working exceptionally well. 31 is just this all-star number that is more difficult. It's like the first one that's difficult to reach. And 31 in general has a lot of fun facts about it. It is, and I would say many of these fun facts come from where it lies on the number line. It's a prime that is one more than a primorial, the product of the first few primes. 2 times 3 times 5 once each is 30, which is one less than 31. And 31 is one less than a multiple of 2, and that turns out to make it what's known as a Mersenne prime, connecting it to perfect numbers. And in fact, 31 just has like a absurd amount of fun facts. Just to refresh a few of the others, skimming through Wikipedia right here, it is all sorts of other primes. Like we see, it is not only a Mersenne prime, it is also a Mersenne prime exponent, which makes it like a related to perfect numbers in 2 different ways. And it is the number of regular polygons with an odd number of sides that are known to be constructible from straight edge and compass. This will be a topic of a future episode, probably not grade -2 though. And a lot of other fun facts. There's the one about pi. Oh yeah, 31 is one of only 2 numbers known that are a hyper 11, as I call a generalized rep digit, meaning in some base it only has the digit 1. And a hyper 11 with more than 2 digits in more than one base. This is one of only 2 known numbers. The other, I think, is 8,191. I could be wrong about that. It's something along those lines. So, look at all these facts when you look up 31. This is a classic, how there's like sequences that you think would contain 32 as a term because they lead up to with 1, 2, 4, 8, 16, and then go to 31. Now, this is something I have made a short about, a particular problem related to circles with that. I haven't explained why that happens, and it actually relates to a Pascal-like triangle. So as we do an episode about Pascal's triangle someday, before long, we will then go to other types of triangles of numbers. So there's other triangles of numbers, and one of them basically will help us see why this is the case. And we have a squirrel back. Good thing I brought some nuts. So, squirrel feeding time. Where'd you go? Where'd it go? Huh. It may have gone over the fence or something, but I'm sure it'll be back. Sometimes when you clack a few nuts together, they can hear that too. And maybe I'll eat a nut in a minute, they'll hear the sound and get jealous. So, oh, we also have another weird snack for later. I wrote this in the description, but I won't show them until the time comes. But I have some very strangely shaped kiwi fruit. Okay, so let me check our comments real quick. And hello to everybody who is chatting. Much love to all of you in all of your areas and all of the moods that you are in. Hope that you are all having a decent day. And let's continue onward with some numberations until that squirrel will probably come back before long. So, right now, an example way we could win is if this pile that represented 1 got tripled and this one that represented 31 got doubled and then digit reversed, and that's where we're at. Now, digit reverse, to make it work best and most strategically, does have an addendum. You're only allowed to digit reverse a number, which means swap the digits of its base 10 representation and go to that number. You're only allowed to digit reverse a number if it doesn't, I was saying here, doesn't end in 0. But if you count or either you could say a multi-digit number not ending in 0, or you could just say a number that doesn't have a 0 in it, if you're talking about the 1-digit numbers as being 2 digits and having a 0 at the beginning. But you can't have zeros in the number, and it can't be 1 digit either to digit reverse it. Now, this is the one that, along with one, well, actually, the other one has a base independent way of phrasing it, but feels base dependent because that's the one about digit complements we'll do in a bit. But this one would take quite an equation to describe what we're doing in base 10 that would be less fun to write on the card and have people try and decode the equation for what happens when we digit reverse that type of number in base 10 compared to just describing it casually. So if we were out here, this one's a 3. This one, the one that was 31, doubled to 62, and then digit reversed to 26. Now, let's say I had these things. Let's say I had a -1, so 26 goes to 25. And then let's say I had 2 +1s that went on this, or these could have already happened. And now that's at 5. And then let's say I have a ×5. Well, I have now made the piles equal. And if that occurs on my turn, I get this amount of cards or points. So, how does this relate to graphs? We saw that we could do some simple ones, like if I take ×2 or 1/2, I can express those by saying y equals 2x and looking at either an x value of 2 or a y value of 2 and seeing where I end up. Like if a pile was currently representing the number 2, playing ×2 on it sends me to 4 because that's when x is 2. What is y? And if the pile is currently 2 and I play divide by 2, which is the inverse of this, it sends me to 1 in a reverse way. If you wanted, you could have made twice as many lines where you'd be writing ones like y equals x over 2 and then you'd only be looking at X coordinates, going to Y coordinates. That'd be a little visually easier, but I find this kind of cool to think about. So we're doing not necessarily the easier way, but, well, it'll be easier for me because I get to write half as many equations. But that's not why we're doing it, that I get to write half as many equations. It's that it's kind of neat that half as many equations cover it. So now we're going to add in some of the other classics. And we add y equals 3x and y equals 5x as multiplicative ones. But it turns out that we can add in y equals 4x, and it doesn't mess up the structure at all. And it's like, why not? Doubling stuff is going to be common. Halving stuff is going to be common. Maybe we need some of these in the mix. I'm still figuring out how many of each of these cards we might put in a deck. You might not necessarily have the same amount of each of these in a deck. Perhaps you could even do it like games like Magic the Gathering do, where you construct your own deck and you get like any of these you can use up to 6 of or something. Maybe you could even use any amount of each of them. I think it would still be interesting strategy to construct decks. But there will be a starter deck I will design to, find a way to sell for as cheap as possible someday. I won't be in that business to make profit. If we get millions of subscribers someday, that's the goal, and then we can make YouTube ad money, and I don't have a rich lifestyle, so I don't need to be charging crazy stuff for card games I'm putting out. The goal, like if I'm making stuff like card games, I want more people to be playing them. That's the whole point of making a card game, is like it's a game. Games are for like people to play, not just for me to think about. So it turns out 4x doesn't mess up what I want, which is that we can't reach 31 and 1. We cannot make them connect in under 4 moves. Now, what would 4 moves here mean? It would mean like you start from 1 or 31. You have dots on those. You can go to any of these lines on either the X value or Y value of what your number currently is. Go to the line and see and like reflect off it diagonally. Not diagonal, more, perpendicular. It'll feel diagonal compared to many of these lines, but technically compared to the graph, we're just going straight and then down. So, or up and over. For example, here, if I wanted to go somewhere in 2 moves, I could say, well, what if I start at 1? And I apply times 4. Well, that'll send me to 4, the graph tells me. And so now I get to plug in 4 if I want. So let's say my next one is actually the inverse of 2 and is a divide by 2. Well, then I would go over to the graph that represents that, which is the red one. And then I would reflect down and see where I'm at. And I'm back at 2. So these keep our structure. What about the additive ones? We have adding 1. We have, and I'll make the colors look more clear in a moment. We'll make all the additive ones be one color and all the multiplicative ones be one color and so on. And, in fact, let's set the range we're working in. We are working in a range where we want X to be, this doesn't describe the fact that we want it to be whole numbers, but we want X to be in that range, basically. And in fact, to be more precise, we could say we want it to be in that range, and we want the same for Y. So let's make these the same color. So we'll just have this in the background. We'll see that the darker patch of the square right there is our target range. And our target range of possible numbers or lines we could be jumping upward or downward in this visualization are the grid points on this scale in this orange thing, counting the ones on the edge. So these will just go hang out on top. We'll turn all of the multiplicative ones red, and we'll turn all the additive ones blue. Now, normally, I was just going to be putting in y equals +1, +2, and maybe +3. And I was like, okay, so these don't mess it up. You can use with all these numerations and all of their inverses, these as minuses and these as divided bys, you still can't reach 31 in less than 4 moves. And that was shocking me already, because with even fewer numerations, 31 had been the smallest number. So like all the numbers less than 31 had several ways to get to them using just 3 numerations, even with smaller batches of which cards were included. And to people leaving questions in chat, I will answer some questions later, but I like doing chat time, but it may be a minute before I get to any of them. But know that I recheck the chat at times. So basically, I was thinking, what other numerations could I possibly add that would not break this 31 thing? Well, certainly I can't just keep going up the chain, can I? Y equals x plus 4? Well, it turns out that you still can't reach 31 in less than 4 numerations with all these. And if I add in y equals x squared and its reverse, square rooting something or going to the principal square root, and if I add in the digit reversal, which we cannot do on the graph today, unfortunately, and if I add in multiple of these digit complement-like ones that we'll discuss in a minute. So there's the digit reverse too, and then multiple more we'll talk about, that with that entire batch of cards, and remember that each of these represents 2, because each of these is not their own inverse. They all have an inverse card. That we still can't reach 31 in less than 4 moves. And the best part is that there is now, with all these numerations, an absurd amount of ways to reach 31 in 4 moves. You can't reach it in less, or sorry if I described that wrong, but what I hopefully have been saying is we don't want it to reach in less than 4. And so all the others could reach in 3. And 31 is the smallest that takes 4 to reach. And so now there's such an abundance of ways to make 31 in so many weird creative combinations using the digit reversals, using squares, stuff, all sorts of stuff. But we're not able to get there in just 3. You can come really close with some combos, but not quite there. Now, we cannot go further with these linearly, in that if I add y equals 6x, or if I add y equals x plus 5, we would be able to get there in 3. So those aren't going to work. However, we are able to add these other digit complement ones. Oh, and plus, so, okay, well, there is one more additive pair that I'll explain. This relates to one of the digit complements, but since it's an additive one, we're going to put it on the graph. We're actually going to allow, since the midpoint of this 1 to 99 range is 50, we're going to allow 50 plus x and the inverse of that. Now, here's where it gets interesting. So I wrote it backwards, which almost makes us think, wait, is the inverse of this 50 minus x? Wait, does this even let me, how can I scroll down these on the thing? Because I'm just blocking what I was trying to show. We're adding 50 plus x. And really it should say x plus 50 to match those. And so we're more clear about what the inverse is, because 50 minus x isn't what I meant to be the inverse of this one. I meant to put x plus 50 and have the fact also be that we have x minus 50. And remember, we would only be able to play x plus 50 on a number smaller than 50 because we have to be in that range, 1 to 99. We could only play x minus 50 on a number larger than 50. These still don't break it. We're allowed to add these in too. But here's the best part. You know, I said, what if the inverse had been like 50 minus x instead? Well, guess what, folks? 50 minus x can go in the game too. Now, here's where it gets interesting, because 50 minus x is kind of close to the way I'm going to express the one that's the digit complement. Now, a digital complement can be in a base a number that adds up with another number to make a certain whole. Like in binary, you might have a 1 turn to a 0 and a 0 turn to a 1 because those add to 1. But say in base 10, if I was looking for pairs that add to 10, then 1 would turn to 9, 2 would turn to 8. Unfortunately, 0 would throw it off a little bit. It would, turn to 10, which wouldn't work for us to do to like both of our digits of a number, or even either of the digits of a number, without it getting kind of confusing. So I figured, what if we look at a number's complement up to 9? And these are going to be actually similar to patterns that would occur if we were in base 9 looking at that same type of complement, like if we were going add up to 10. But we can do it in our base, and we can just say what number with it adds up to 9. Now, in this case, it works a lot better. They all line up with 1. 4 and 5 work. 3 and 6 turn into each other. 2 and 7. 1 and 8. And 9 and 0. And now they all line up, so we could maybe apply that to both digits of a number. I thought about whether we could include applying it to just one digit of a 2-digit number, only one of them turning to its complement. However, doing that broke the rule that I was looking for. It allowed me to get to 31 in less than 4 steps. So those didn't work. But it did work when I applied it to both digits. Now, you might think that sounds weird to graph. Making both of the digits of a number add up or turn to whatever their complement in terms of the number 9 is. Whatever 9 minus them is. But then you could think, wait, if I'm saying 9 minus each digit, what I'm saying is 99 minus x. And 99 minus x turns out to be this sort of digital complement because we're 1 less than the square of our base. And so you would get maybe another pattern in like base 8. If you looked at 80 minus x, might be representative of some base 8 pattern of sorts. So these are what we have on our graph. These ones, interestingly, are self-inverses. They don't have another card that's their inverse because if you play them again, you get back where you started. They're their own inverse. Let's say I was at the number 7. 50 minus 7 is 43. 50 minus 43 is 7. I'm back where I started. Same with this one. This one has a different inverse. This one's inverse is x minus 50. And again, sorry, digit reverse. We cannot fit you on here, but there is a card that is digit reverse of a number that does not contain the digit 0. And that we would have to put as a little dot-like function instead of lines because, that's not going to work on like a whole continuum of numbers with irrational numbers and stuff in there. Let's digit reverse pi for Pi Day. Okay, anyways, this is the range we're looking at, and these are some numberations we're allowing. How the heck does this graph let me test things about the card game? let's remind it with an actual test. Let's say I want to get from the number 1 to 31. Let's say I'm only going to be playing things on my 1 pile to turn my number 1 into my number 31. Well, let's say to turn the number 1 to 31, first I go to 1, and then these are possible, and we would have to zoom out to see all of them. It's hard to get them all on screen, like, to see the ones we're actually going to want to look at probably down here and analyze that zone. These ones all the way up here are the 50 minus X and 99 minus X, those diagonal flying ones up there. Zooming in and losing those for a moment, let's say that from 1, I do times 3. Well, I went from X, and I have gone there because we have sort of the positive directional feeling ones, the enhancing ones as what we have in here. And we would go from Y to X if we're doing sort of a shrinking one. In most cases, that doesn't apply to, these ones at the bottom. But in most cases here, the shrinking move, we would go from Y and then look at X. And a growing move, we would go from X and then look at Y. So I have been told by the graph that actually that's funny. There's 2 functions that hit right here. So he was actually thinking that I was talking about X plus 2, because there's 2 ways I could have started off to turn my 1 into my 3. I can get there with either times 3 or with plus 2. Either way, I am now at 3. And let's say from 3, I want to go somewhere. And let's say from 3, I apply a plus, what are we going to apply? Let's apply a times 2. So where's my times 2? That's this one that got a little bolder. And if I look from 3, that's where it meets. That leads me to 6. Now, from 6, let's say that... Now, this is going to be a kind of boring path there if I went to times 5 and then to plus 1. That is one of the simplest paths from 6. Let's do one that's going to enhance us quicker so we can sort of use the graph a little more. Let's say I had actually gone with my moves times 5 right away. And that's not necessarily better. Like, being on that 6 right then was fine. I could have times 5 plus 1. There's even, other maneuvers that may have worked. I'm not sure if there's other ways from 6 to get there in just 2 more, but at least that would have worked. So bigger is not necessarily better, because times 5 can only be played on 19 numbers, whereas times 3 can be played on 33 numbers. But in this case, we're getting bigger just to use some of the weirder ones as an example. So now I'm at 5, and let's say I do something weird. Let's say I do, I don't even know if this will let me get there in 4 steps, because we're going to be trying weird stuff. So we'll see how many steps it takes. It's been 1 step. Let's say I 50 minus exit, and now I'm at 45. How do I know that? By going from 5 all the way up to the one that says 50 minus x, and seeing that where those meet, where that it's 5, it's not really a meeting. I guess it's the only one right there. It's because it's the only way to get from 5 directly to 45. We don't have a crossing right there. So we're now at 45. Now let's say we shrink it. So we're coming from the y-axis, and then we're going to bounce down to the x value. So from 45 to shrink it, let's say we do a divide by 3. This is going to be our 3rd step. The path that I'm taking, I think, will take 5 steps in this case, which will often work in the game. But there is a huge variety of 4-step paths that you folks might have fun, like investigating on your own time just for fun. How many paths with just 4 steps can you imagine? And you don't need to necessarily take your 31 and shrink it while you take your 1 and grow it. Because of the inverses, you can just work from 1, go upward with each of these, and it will be describing many paths at once that could have been inversed from the other way for part of its work. But you can just go from the number 1 to get to 31, kind of get all the data. Then you'd have to know each of those could have been backtracked instead of just uptracked or met in the middle in some way. So in this case, we're at 45, and we're going to go to our divide by 3 line. Where is that? That's the bold one there. 45 hits it at 15. Now, obviously right now, the things the graph is telling me seem kind of trivial. I could have done them in my head. That's because we're doing a graph based on a really simple version of my card game that I want to be fun for non-mathematicians. I don't want people to have to be doing crazy equations that you'd need a graph's help for while playing the starter version of this game. That's not going to help make math more catchy. You know, this should be a game that gets people to like math even if they previously didn't. Not necessarily a game that you need a graph to figure out the next number of. With that said, the fact that we could use the graph to get the correct data is really interesting. The fact that it went 2 ways, x to y or y to x, if it's a bijective function, is very interesting. And if we had other questions about numerations, which I'm sure I will in the future, maybe some mathematical questions I have, a graph will be able to help me with, even if it's not necessary for our card game here. But to show that it works, we are now at 15, and from 15, what we'll do next is we are going to add 3. That would, if I go to the +3 line from 15, I would get to 18, and then I can, oh wait, no, not add 3. What am I thinking? Where do I want to go? We don't want to be at 18 necessarily. We'll add, let's say, a quicker path would be if we added 2, getting to 17, then we times 4'd, getting to 28, and then we +3'd, getting to 31. Now, a good way that I realized to think about this, if you want to track how many paths you can find, is do a little work from each direction. I said you could just build upward from 1, which is true, but it was easier, I realized, to see, okay, what numbers could I get to with 1 step from 31 and a batch of numerations? Which ones could I get to from 1 and 1? And actually what I did is from 1, I applied 2 numerations with 2 numerations, one after the other. What were all the possibilities I could get to from 1? Because from the first numberation, there's a limited amount of things I can turn 1 into. I can turn it into a 2 different ways, a 3 2 ways, a 4 2 ways, and a 5 2 ways. So there's a kind of nice symmetry there that even though they look different, that these go 1 to 4 and these go 2 through 5, from your 1, they kind of line up in doing the same thing as another one if you're starting with 1. Then from 1, this wouldn't affect it or change it. And this would send it to 51, this would send it to 49, and this would send it to 98. So I was so shocked when I let 1 turn to 49, 51, and 98 in the first move, and I still couldn't get to 31 in under 4. This is something I'm still testing, so there's the smallest chance I'm mistaken and that 1 numberation was 1 too many, that one of these could need to be taken out. But I've been looking long and hard, and I've even been trying to write down all of the possible paths in a simplified way, and I'm pretty sure there are no 3 paths using all of these, and that there's an absurd amount of 4 paths. Even if you don't count the inverses, even if you just say we were allowed to play on the 1 pile to turn the number 1 into the number 31 using these and the digit reversal. And remember, these top 2 aren't even numberations. These are just to show what range we're talking about. I don't even think it helped because we were so zoomed in. So let's just get rid of those. So there's an absurd amount of ways to get there because from any of those starting points, you can do different things from being at taking your 1 to a 2, 3, 4, 5, 49, 51, or 98. What could you turn the 31 into? Actually, a lot less. We can digit reverse 31 into 13, and that's really helpful for a lot of paths to either be, your starting or finishing move, kind of like where those paths meet. We can use these on it. So 31 here would turn into a 68. Here would turn into a 19. Here we could use this. It would turn into a 81. And then we could even do something like square root it. Like if we didn't have any times 3s and I wanted to get to 9, I could like plus 50 by 31 and then square root it to 9. And then divide by 3 twice. That's a 4 path. And the way we would do it here, if we're just talking building up from 1, would be we could say, the way I did that is times 3 square minus 50. Because this one has an inverse, which is x minus 50. Now, let's see. We're not going to go into all the 4 paths. We'll see if that makes sense to start writing them down. I did, bring a document in case we need to. And of course, as usual, we have some whiteboards in case we need to write down some of these 4 paths in a minute. I need to run and grab some water. My voice is getting pretty dry, but I'll be back in just a minute or two. You're just going to have to listen to the birds and small chance of squirrel. There are some nuts on the table. I'm going to leave the nuts on the table closer to the camera. So if a squirrel takes these nuts that are right here, you will see the squirrel for sure. And enjoy the bird sounds for a moment. I'll be back shortly. We may write down some numberation paths, or we may just discuss some other cool things that I found about these graph connections, which types of 4 paths work, which other numerations could be added if the game was expanded upon. And, for example, there are many numerations that do things like reverse the order of things in a stack or switch something from one stack to another. And while those are fully valid, because a stack, you can currently read its number just by going upward and seeing whatever it currently creates, they're a lot harder to track in person. So some of those I might save until if I make a digital version. There's also other numerations that I want to add that just might be too complicated for the starter set, but that I still have to test if they would screw up our 4-path thing or not. Like, am I allowed to add triangulate, where it goes to the triangular number of our input, which we could mathematically write with their formula, which is n times n plus 1 all over 2. And its inverse would work. We could untriangulate something. Would that work? Would that fit in? Or would that make 31 now have a 3-path? We don't want any 3 paths because that makes luck be more involved. That makes you hoping to draw whatever cards are involved in that 3-path. Right now, with how many 4 paths that I've found, I don't even know which of these numerations are better, in quotes, than others. I do know digit reverse seems to be pretty good and important. You could pull off some cool stuff with that. So leave a comment with any 4 paths you can find if you want, or just hang tight. I'll be back shortly. And I'll also show you when I get back, apart from chatting about this, some very strange kiwis for a sort of little snack break. Alright, folks, I'm back. Hope you enjoyed some bird song. Now, I did get a little water, but I decided don't need to fully refresh my mouth. Maybe I can refresh my mouth with these strangely shaped kiwi fruit. Now, I have filmed with these before, and they show up every once in a while at a particular season at one of my local produce stores. They're like two kiwis that decided to be one. Sometimes you get like they're closer together and it's just like a double one that's just really thick. This one's almost like heart-shaped. And sometimes you get this whole stretchy thing. Some of the other ones that didn't seem as ripe look more kind of like you could see the divide even more. It's like two connected. And I don't know why this tree decides to do this, but when you look at the batch of kiwis that they have from this producer at the store whenever they happen to be in stock, like almost all of the kiwis are like this in that batch. So there's some tree or farm or something where all the kiwi fruits are coming out like this. So also to those who don't know, surprisingly rare fact. Okay, I probably should have rinsed this off first, but I'll wipe it off with my sleeve. I don't know if that's helping or hurting. Anyway, many people don't know, but the skin of kiwi fruit is edible. Now, it's true that you might not want to eat a ton of it, because they probably don't worry as much about putting pesticides and stuff on the outside of fruits that they don't expect people to eat the skin of. So that was a disclaimer that I gave in the whole episode I actually made not that long ago on the Combo Class channel about rare fruits. Let me make the camera bigger so we can see these better. But of rare fruits. It wasn't actually about rare fruits. I'm thinking about that because I'm holding rare fruits. But the episode we made was a rare fruit-based episode, but it was actually about common fruits that people do not know you can eat the peel of. But it turns out you can. Although I did give the disclaimer, like some comments also did, that you got to be more careful about eating the skin because, you know, like if they don't expect you to eat the skin, they're not as worried about keeping it pesticide free and stuff. But to note, we did an episode about that not long ago about fruits. And this is the episode that you really should watch after the stream ends if you haven't seen it yet, because that came out 21 hours ago and has a lot of clocks, a lot of math, a lot of chaos. It's sort of the third in a trilogy I've made because I linked the others that it's related to in the description and in a comment on it. But back in the day in grade -1, and by back in the day I mean like not that long ago, like a year and a half ago probably, maybe even just a year ago, there was an episode that was... Where the heck? I keep missing it. Modular multiplication magic. This was kind of the first time I introduced modular arithmetic on the channel. Since then, this episode relates to it in a way, and this episode relates to it in its own way. This one here. But the second of what I would call more of like a trilogy would be, since that one was about modular... Oh, the squirrel's back. Does it want any kiwi? I wonder if it likes kiwi. I'm sure it prefers a nut. Oh, there's some kiwi juice on the nut. Might taste some while it's cracking it open. Let's see if it just hangs out to eat it. Some of them just hang out in the classroom to eat their nuts. Nah, he ran away. But there's at least one that whenever I give it a nut, it'll just like perch right over there and chip open the nut and eat the whole nut right there. And I think it's because it knows that it wants to eat one and then get a second one to carry away and bury or something. And it can only hold one at a time. So it comes and gets one from me, and then it comes back to get the other one after it ate the first one. So it doesn't want to go too far. Anyway, the second of the, quote, trilogy of modular stuff would be when we did modular division, after the first one being the modular multiplication. And this one is modular exponentiation. And it does relate to other cool things, like you can see the word pseudo-prime right there. That almost could have been... Like, the episode almost could have been called something about pseudo-primes and then had the text on the thumbnail be that it's about modular exponents, because those are a rather large part of the episode, too. Although it's more about the clock-like exponent patterns. Then when we look at some prime mods and bases, we do encounter things known as pseudo-primes as well. So make sure to catch up on those after the stream. But right now, what I want to note is that this will be our last stream for a little bit while I'm talking about this card game, because I've done a few streams in a row that were kind of related to it. And so come back to this stream if you've found anything cool, if you play around with this type of thing on your own. If you just have any findings, like for now, if you're bored, you just comment to 4path. You know, any comment helps. Not necessarily even on the stream, like comments after the fact help even more once it's as a video. But especially if you want to try and calculate how many 4paths there are. Whether you want to start from how many are 1 to 31, or whether you want to factor in for each of those how many of them the inverse would work for, which I guess might be the same number. We might be able to do a deduction of 1 just to 31 and then multiply it by a constant, but I'll have to think that through a little more. The amount of 31 paths to 31 from 1 or vice versa is quite large. So let me know if any of you play around with that more. And I'm going to think more about this thought that struck me the other day of how we can take numerations on a graph, and if it's a bijective function, then we only need half as many lines. So the fact that you could graph these, I'm sure had crossed my mind before, but the half as many lines thing only struck me recently, because maybe only recently did I kind of confirm in my brain that in the starter version of this game, I want every card to have an inverse, whether it's a different card or itself. And remember, our intuitive sense of what an inverse means in this game is that if a pile represented a number, if you play a card, there should be another card you could play that sends you back to the number that it was at before. That undoes it in a way. So those are some things to think about. Now, I might actually wrap up the stream before too long. This was going to perhaps just be closer to a 1-hour stream. So let me go through the chat, which always distracts me for a while. Let me have one more bite of this, but perhaps without the skin this time. I know I said 1 bite, and it took like 3 bites. It's really good. Okay. Anyway, looking at our chat, thank you all for leaving random comments and thoughts. Let me put it back up to me so I can make the chat look bigger without having it all over, having the stream look weird. So someone asked earlier, I don't know if they're still around, if any of my family are mathematicians or academics in general. Both of my parents have been teachers at times. My dad is a teacher he's taught various grades. The most common one he taught throughout life was 5th grade. So I wouldn't say he's a mathematician. He's interested in math to a degree. He likes math more than the average person, for sure. Perhaps not to the degree I do. My mom is a bit less of a mathematician, even though she still finds like my episodes interesting and stuff. Like that level of like recreational math she can find interesting when it's, you know, trying, not teaching you level 4 of a college course, but trying to make something as understanding as possible. She could enjoy stuff related to numbers, but maybe less of a mathematician. And she has been a teacher. She would more on the art end. She's been an art teacher and graphic designer and stuff. And so I would say I do come to a degree from a family of teachers. And somebody asked, are we seeing line intercepts as number of moves? And yes. And somebody wrote down equations for how we could try and describe digit reversals, I think, which is cool. And somebody said this could function as a playing board. And I did like the idea of a pegboard. Like some old games like cribbage and stuff, you have like a little wooden board with holes in it and with little pins that sit in the holes. And we wouldn't necessarily be doing a line intercept version of it, because then we'd have to have, it might work, but remember that some are small scale and some are big scale because we have 99 numbers. And so, like, I mean, I guess none of them are huge scale, but these ones are big scale compared to the intricities down here. Oh, no, wait, it wasn't even showing it. But yeah, I was saying, like, these intricate details would be hard to have on the same physical board as these. Or to have the board be this big. I mean, the board could be bigger than this, so it could work. But I was thinking more like the board would just be a series of numbers. It could be just a 10 by 10 grid, and that you would more just use it for, like, where do I hop my numberation? And perhaps on there, it might have some of the numerations could be linked in a way, like perhaps ones that are twice as far apart from each other. If you imagine it as a number line, I don't know if it would physically make sense to have it be a line with, you know, 1 through 99 all on separate things on a line. That'd be a rather long game board. It'd be kind of hilarious to get a board game that's like a rectangular prism that's like not that big this way, but really long. So that's probably not how we're going to design the starter set. But if you imagine it as a number line, then you can imagine a visualization of that, of which ones have or could have which numerations played on them, at least, so you know, like, what creates a valid number. For example, the first 19 numbers can be doubled. The first 19 numbers can be times 5'd. The first 33 numbers can be times 3'd. The first 49 numbers can be times 2'd. And each of those is the same amount as their inverse can do, because there's the same amount of even numbers from 1 to 99 as there are all numbers 1 to 49. There's the same amount of 3-even numbers from 1 to 99 as numbers that can be multiplied by 3 and be in that range. So, because it's bijective, they line up one by one. So I still don't know really if times 5 is better than times 2, or if it's like too clunky, like it gets you too far and you can't use it as often, because you can use times 5 less than half as often as you can use times 2, but it changes things on a bigger scale. Perhaps that's why digit reversal was so powerful. You could use it on a lot of things, but it could change things on a big scale. 99 minus x can do crazy stuff too, because if you imagine, we said from one move I can get my 1 into a 2, 3, 4, 5, or 49, 51, or 98. So just counting the 1 through 5, after 2 moves, I could apply one of these, and I could be anywhere from 45 to 50, or anywhere from 45 to 55, actually. I could be anywhere from, 95 4 to 99, and so much more. You can hit pretty much all the numbers. There's some others that are like 31 that take 4 moves to hit. I don't know if that's even still the case, which ones are left. There's got to be others, but I don't even know which ones from 1 through 99, apart from 31, can't be hit with 3 of these, and with all of the inverses and with digit reversal. So 31 is doing really, really good. I have to like triple check that 31 doesn't glitch on like none of these new ones I added do somehow fit into a really clever 3 path, but with just these, the inverses and reverse of digits, I think you can't do it as far as I know. And that makes 31 such a good target number that we get to see some of your names here. Some folks get lucky. Let's let everyone get lucky if some folks are going to get lucky. Well, now we passed everyone's name. Oh, except for who was at the bottom. We didn't get to see all their comment. Okay, everyone's lucky. Now, sorry to anyone who tried to leave a comment in response to that because the stream's a little delayed. I've already moved the thing. The stream's delayed a second from when the chat comes. Or from when you get to see it. I mean, which makes sense. I get to pick how much delay there is, but you actually usually want to pick a medium amount because I don't want it really delayed for you folks, but I want to give it time to come across as HD. If I go like hyper quick, it's more likely that it could look blurry. So, but I don't know the details about that. I need someone on my team who knows the details about that. So, you know me, I'm the old school design things on playing cards and like the simplest free graphing calculator software type of guy. So I'm the ideas man. I am not the technology man. In any case, I think that is most of our stream for today. For some other thoughts. Oh, somebody said it took a nut while I was gone. That's cool. If that's true, I'm going to look back in the stream. And if that's true, that's awesome. Because, you're right. There were 3 here. There's 1 now, and I only fed it 1. You're right. Yeah. For a second, I was worried that you were like trying to prank me or something. But that comment must be right because there's 1 nut left and there were 3. So it did take 1 while I was gone. That's pretty cool. I'm going to have to roll back this clip. That's a new one for me that I get to see a squirrel video in my classroom that I don't know yet what it's going to look like. So, and whoever said thief, hopefully you don't mean me. I don't know why you'd mean that because I am not a thief. If you mean the squirrel because we're chatting about it stealing nuts, I wouldn't consider the squirrel a thief either. We sort of have a deal that if I leave nuts out in the classroom, I expect them to be gotten. Now, I bought a comically large bag of nuts and I kind of did something dumb that kind of ended up making the squirrels get all of them really quickly. So that will appear in the squirrel episode at some point later in grade -1. That's one of those clips I'm saving for a future episode before I show you. So we are 3/4 of the way through grade -1. As we can see, the classroom is falling apart to a degree, but the desk apparently still has 4 legs. That's what this is sitting on. Thank you all for joining me. I'm going to wrap up here and jump to other things. Somebody said that they're surprised I'm doing it in base 10. It's, I would like to make versions in other bases, but I want this to be a game that gets non-mathematicians able to appreciate numbers. So non-mathematicians are not going to want to have a calculator for a lot of the moves for them to calculate, okay, what is this number how I know it's written? What does that mean in base 6? Almost all of them are base independent. So really, we were even able to describe digit complements as some number minus it. In this case, it won't always work. but digit reverse is sort of the only one. So I have certainly thought about if I, make a version of this game to sell, having the main starter deck and then having some side ones that are like slightly more complicated cards that you could put in the deck if you want. They would have the same backs, but they would come separate. So, you could shuffle them in if you want. And those would include things like take this number, go to its representation in some base, swap the digits, then go to the number that would represent in general. So a digit swap that's not in base 10. There are other things we can do with digits, but for now I wanted to keep it to things that were bijective, that were 1-to-1. So I couldn't do something like go to its value mod 10, because then, or any mod really, any useful one in this case, because then there would be multiple numbers going to the same spot and it wouldn't have an inverse card, because how would the inverse card know which of those multiple numbers to send that thing back to? Similar to if I included negatives and still had the squared card. So if I included negatives, I thought about it. The squared card would have to be phrased differently, and then you would have a way where you could make it end up having the same sign, and that you square its absolute value but keep the sign, essentially. So there will certainly be expansions of this idea, hopefully, if I ever do anything with this, because I, can get distracted by new ideas and old ideas. But I'll try and wrap this up into figuring out how many of these cards will be helpful in a deck on my own time. And if any of you play test it, that could give some important data as well. Now, somebody said they're editing a video for Pi Day 2. That's awesome. Oh, there's another squirrel that just ran by. Does it want the final nut? So, somebody said they're currently editing a video for Pi Day. That's cool. Keep up the good work to everybody who makes educational or entertaining videos. Entertaining as long as, certain types of entertainment. That would take a while to explain, what entertainment I actually find both enjoyable and morally good. But educational content is usually morally good, and whether or not it's like entertaining, which is a goal for it to be as well, but even at times it isn't, the fact that you're learning is very important. I don't know this channel, so maybe I'll check it out. And I will drop something for Pi Day myself. To some people it may be Pi Day already. For me, that'll be tomorrow. I'll probably put out something for Pi Day then. Not sure what form it'll be in, if it'll be a live stream or a bonus video or what. And I think that's about all. Make sure you've seen the new combo class episode that is linked in the description. And I'm hearing more squirrel noises, but sometimes they can take a while. So I'm going to still wrap up here and just, you know what? We will leave this nut here as an offering and reminder to the squirrels that this table is a safe place for squirrels. We'll leave it on the table because I like encouraging them to have to come up here. In fact, we'll put it right in the middle of the table on this giant scorched burn mark. And right in the middle of the table on this giant scorched burn mark should be a good spot to help convince the squirrels the table is harmless, which it is. I mean, it's not harmless to everyone. It's harmless to them. I won't let it hurt them. So that's about all for this live stream. Hope you all enjoyed. I have a little bit of cleaning up to do in addition to the other projects I'm working on. All the clocks spilled. I've put up some of them back. In any case, I will be back again soon for some form of pie-related thing tomorrow, and or posting some sort of short on this channel tonight, because I have gotten back into making and posting shorts every couple days on here. And pretty soon will be the time we get back into making bonus videos on this channel. Though I've only not been doing bonus videos because I've been doing all my editing these days, and I've been doing kind of complex, long episodes on the Combo Class channel that use all of my editing energy. And then so when I have other thoughts to share, I often am like, I'm just going to live stream it. I don't want to do any other editing right now. So before long, I will either have, the mood to edit some bonus stuff, or other people helping me edit some of the Combo Class stuff, giving my brain more editing time and space for me to work on those in some shape or form. We will get back to making bonus videos that are like more digestible streams on this channel as well. And whoever said they just got here, don't worry, my streams are saved as videos, so as soon as it ends in a moment, it will be watchable still, as well as my many hours of live streams that we've done in grade -2. All right, folks, love you so much, and I'll catch